We're ready.
Okay.
It's not right.
All right, everyone. So let's go ahead and get started. I'm excited to introduce Juliana Harr, who's been in my research group for the past 2 years. Juliana got her Bachelor of Science at the University of Illinois, Urbana-Champaign in physics, and she took some classes in atmospheric science that she really enjoyed, so she switched over to our side. And she actually was going to go to the professional master's program, but as funding does, it was very late, and I'm like, okay, I need a student, and I decided to steal her from the professional master's program, and I'm really glad I did. It's been an absolute joy working with you, Juliana. Today she's going to be presenting her master's thesis on using linear inverse modeling to examine some QBO relationships. So I'll let you take it away.
Can everybody hear me okay? Okay, awesome. So yes, I'm Juliana, and we'll be talking about using linear inverse modeling as a tool to diagnose some of these relationships here. And just a little bit of an overview of what I'll be talking today. First I start with an introduction, give a little bit of background about the QBO, the MJO and ENSO, just in case anybody's unfamiliar, and then talk briefly about linear inverse modeling, because I know a lot of you probably haven't seen that before. Next I'll be talking about the data I use, as well as methodology associated with deriving the limb, building the state vector, using dynamical filtering, and forward integration. And then finally I will show some of my results, including Havmala diagrams, power spectrum plots, as well as some composite maps. And then I will finish off with some conclusions and future work. Okay, so the Quasi-Biennial Oscillation, or QBO, refers to a pattern of downward propagating winds in the tropical stratosphere, which alternate directions between easterlies and westerly, the two phases of the QBO, which will now be referred to as EQBO and WQBO from here on out. It has a period of approximately 28 months, which is where the quasi-biennial part comes from, because it's almost 2 years. And as the QBO winds propagate downward, they lose a lot of their momentum, so they need a driving force behind them to sustain the processes happening. And this is supplied by Kelvin and Rossby gravity waves. Rossby gravity waves produce a net easterly acceleration that's really helpful for EQBO, and Kelvin waves provide an upward flux of westerly momentum for WQBO. And then a really useful way to visualize QBO activity is with using pressure versus time heights to show how the QBO waves are moving through time. So as you can tell by the slight slant in the data, that actually shows the downward progression. So as time is going forward here, you can see that they are in fact descending based on the increasing pressure levels. And then we have the negative anomalies are associated with EQBO, which are shown in blue, and then the positive anomalies for WQBO, which are shown in red. And it's a little bit difficult to tell from this diagram, but the easterly phase of the QBO tends to typically be stronger due to an upward advection of momentum that effectively traps the winds up in the stratosphere and keeps them from weakening. And then on the other hand, the westerly phase is associated with a downward advection of momentum, which means it's typically a faster propagation and more regular as well. So moving on to the MJO, or the Madden-Julian Oscillation. This is a large-scale convective system in the tropics. It propagates eastward at about 5 meters per second with a 30 to 90 day period, and it is called an oscillation, but it's pretty irregular, so that's important to note. And its main features are cycles of enhanced and suppressed convection and precipitation, and it's also a very important part of tropical intraseasonal variability, not to be confused with interseasonal variability, which is longer time scales. This is much shorter. And it also is very important to recognize the coupling between convection and circulation, which is crucial for MJO maintenance, as well as atmosphere-ocean coupling, which is very important because warm SSTs tend to support deep convection, which is necessary for the MJO, and provide energy for the cycles. So just to visualize, I have column integrated heating anomalies plotted here, and phases of the MJO are determined by RMN indices, which use outgoing long wave radiation anomalies and zonal wind to kind of determine the evolution of the MJO and where it is spatially. So as you can see here, the red, which is positive heating anomalies, and the blue, which is negative. So typically, you have the region of suppressed, followed and preceded by enhanced convection and precipitation, and vice versa. And you can also see by the blobs of color here that it is in fact propagating eastward over time. So how exactly does the MJO and the QBO connect to each other? We have found a significant connection throughout boreal winter, so December, January, February. One study found that roughly 40 to 50% of interannual variation in MJO amplitude could be attributed to the QBO. Also, MJO activity tends to be stronger and more predictable during the easterly phase of the QBO. The easterly phase tends to be more favorable to deep convection development, which is necessary for the MJO. And the MJO is also initiated more frequently throughout eastern QBO phases, as well as propagates slower, which leads to a longer duration of MJO events. And also, it is more likely to propagate further into the western Pacific and over the maritime continent, which is typically a barrier to MJO convection. The QBO can also influence the MJO teleconnections, such as MJO tends to modulate the North Pacific storm track, and these changes are typically larger in amplitude during the easterly phase of the QBO. And also the MJO is pretty strongly linked to the North Atlantic Oscillation, and these connections are typically stronger during the westerly phase of the QBO. And also, structural differences of the QBO and its phases tend to impact the relationship as well. For instance, temperature anomalies during the easterly phase of the QBO tend to be more in phase with MJO convection, and they help to reduce the static stability of the troposphere, which also promotes convection for the MJO. And then if we look at column integrated heating again, but this time divided by the phase of the QBO to see what the activity looks like. Again, sorry, I had to kind of squish them on here, so it's a little bit hard to tell. But during the easterly phase, you can actually see that, at least in fact, the positive anomalies do appear stronger and kind of bolder. So yeah, so stronger during the easterly phase. And then moving on to ENSO, which I'm sure you've all heard a lot about. This is Earth's leading pattern of interannual variability. So that refers to its much longer period and time scales, which could be anywhere from 2 to 7 years. It's characterized by irregular oscillations in sea surface temperatures, thermocline depth, tropical convection, and air pressure. And it also has a lot of flavors or diversity. So you see a lot of variation from event to event, year to year, a lot of variation temporally, spatially, and in amplitude. And warm events, so El Niños, tend to be more diverse as well. And another important fact that when analyzing ENSO, the events kind of depend on the index being used, which tell you a lot about location and the type of event. Okay, so moving on to the relationship between ENSO and the QBO, it tends to be very dependent on the period being sampled. A study found that the QBO amplitudes were larger during cold events, so La Niñas, but this was only after the year 1990, and it had the opposite correlation before. So a possible explanation for this could be due to a broader gravity wave spectrum that was occurring during La Niñas that led to bigger QBO amplifications, but deep convection was likely stronger during this period, but kind of switched before that. And then also, it's pretty difficult to distinguish ENSO effects on the stratosphere from QBO, especially when looking at factors like the polar vortex. One study found that the ENSO and QBO tended to coincide during a lot of these events. And then ENSO could potentially modulate a propagation during the westerly phase of the QBO. There's a study that found that ENSO was enhancing westerly wind descent, perhaps. Kelvin waves are also really important to kind of easing this relationship and helping with the descent. But they found that the rate that the waves were descending could not be achieved by solely Kelvin waves. And then, so moving on to some current challenges we face in studying these relationships. Models like GCMs really struggle to capture the QBO and especially the QBO-MJO link accurately. Even when the QBO is well simulated, they find not really many significant differences between the easterly and westerly phase of the QBO during MJO events. Models typically tend to underestimate QBO amplitude, especially near the tropopause, and they have a really weak temperature anomalies that are associated with the QBO that are kind of necessary for understanding it. And there's also a lot of failures in tuning gravity waves, which are important for building these models. There's a lot of time period dependence and inconsistency, as discussed before. And also, there's a lot of limited sampling in the observational record, especially when looking to remove the effects of something like ENSO, you find even less data to work with. Okay, so why are we using linear inverse modeling then? Well, this guy's 2 minutes. So using LIM, you can derive a dynamical model empirically through observed statistics rather than just relying on theory. And then coarse graining data, which is taking averages over large period events, tends to make systems more Gaussian and predictably linear. And also, LIM can be used as both a forecast and a free-running climate model. So when we use it as a free-running climate model, we're able to supply a lot more data that would help with the limited sampling problem. And then one technique that I will talk about soon, dynamical filtering, helps you to isolate a lot of the processes happening, which makes analyzation a lot easier as well. So now the main objectives of using LIM in this study is how can we, how does increasing the sampling size affect the nature of these relationships? So that will be using the climate run portion of the model. What sort of nuances does dynamical filtering bring out in the data when we kind of separate everything? And then how does the individual variability of these phenomena affect their connections to each other? Okay, so a little bit of an overview on LIM. Lots of big equations, but I'll do my best to kind of explain them well here. So LIM examines the properties of a dynamical system via the observed statistics, as mentioned before. This is a big equation that we use here, where x is the state vector, L is the dynamical system matrix, and then that eta there is noise. So basically, this portion of the equation refers to the predictable dynamics, and this is the unpredictable part. And we also use propagator G, which evolves from an initial condition, x of 0, to a final condition, x of t. And by using this, as well as the covariance matrix of x at the initial condition and the final condition, which is at a lag that we will determine later, we can kind of backward solve for L. And also the state vector x will evolve in time according to the solution to the homogeneous term. And also L represents the linear dynamics of the system as well as a linear approximation to the nonlinear dynamics. Okay, so moving on to the data used for this study, it was JRA 55 data. It initially had a resolution of I think like 1.25 by 1.25, but it was regridded to better capture the features being examined in this study. It was also originally on 6-hour intervals, but it was averaged to get daily values, and it goes from the range 1958 to 2018. It was sliced between 25 south and 25 north to represent tropical latitudes, and these are the variables that were used from JRA 55. A 5-day running mean was applied to them beforehand, as well as the climatology was removed in the seasonal cycle to get the anomalies. So we have sea surface temperature, column integrated heating, 30 and 50 millibar zonal wind values, and the 750 hectopascal stream function. And SST and heating are really, really important for capturing MJO and ENSO features, and zonal wind is critical for the QBO. And also, we include both 30 and 50 millibar in the state vector because it helps to capture the downward propagation. So moving on to building the state vector, which is our x of t, it's expressed in reduced EOF space, meaning that only a specified amount of variance is retained for each variable. So for SST, we kept 53% of the variance, which was explained by the leading 8 EOFs. For heating, we kept 34%, which was explained by the leading 30. For zonal wind, we kept 93%, which is the leading 4. And for psi, we kept 56%, which was the leading 7. So this gives us a grand total of 49 principal components to work with. And these values were chosen based on similar studies that were using LIM, as well as what was necessary to retain the numerical stability of the model. Okay, so moving on how we chose our lag value. This was used with a tau test, which is from Penland and Zardishmuck. And it's selected based on the results of this test, as well as the time scale of variability that we're looking at. So the curves here represent the Euclidean norms of submatrices Ln of L. They're the submatrices of L for each tau value. We have an axis here of 1 through 20 days of tau. And L needs to be independent of the chosen tau because there's a greater risk of error when the lag is larger than half the period of smallest oscillation. So we see that big peak at around 15 days would be a very poor choice. And we're looking for values that are smaller than that. And we chose 5 days given that an MJO period, or the phase of the MJO, is typically this long. And we don't want anything that's too big that will kind of like affect the timescales of what we're looking at. So our next step was to apply dynamical filtering. This was following an equation from Penland and Matrasova, where we're decomposing X based on the eigenvalues or the eigenvectors of L. So grouping for each filter is based on the amplitude of each eigenmode, as well as the inner dot product of the equation here, where alpha sub j is the projection coefficient, U is the eigenvectors of L, and J would be the 49 modes that we kept in our data. And we'll examine the e-folding times and then sum over the specific modes that fit into our filters to kind of like supply the data for the filters. Also, another important thing to remember is that the modes of L tend to be non-orthogonal, which can lead to a lot of interference between subspaces, which we'll see in the next couple slides. Okay, so here we have the relative variance contribution for each variable to each eigenmode, as well as the filters and the eigenmodes that they contained. There's doubles because they contain both real and imaginary ones. So for instance, kind of the way we decided, so for the modes that would be internal to the stratosphere, we know that they must have a really high variance in zonal wind. So if we look around here, I have a laser pointer. Almost forgot. So 44 and 45, you can see that pretty much all of the variance is contained in zonal wind. And for some of our other filters, such as the stratosphere, troposphere, SST modes, we're looking at modes that have kind of shared variance in SST, like as well as Q and U50 as well. So we're looking at like 42 and 43, and then 46 through 49, so kind of all around here. And then we also have our modes that are internal to the troposphere, which is where the MJO lies, and additional modes that have shared variance in SST and Q, which is our troposphere SST modes. So the companion plot to this would be plotting the e-folding time versus frequency for all these modes. And based on the frequency and e-folding time, we can deduce which modes are explaining which dynamical processes that we're looking at. So this mode up here, which is one of our stratosphere internal modes, we're deducing that is representative of the QBO. So if we plot a spatial pattern of the QBO zonal wind, that's what that looks like. And we look at the e-folding time, frequency, and period to see that this long period would be representative of QBO phase, and kind of a low frequency as well. So if we look at some of our other modes here, ENSO would be contained down here in these blue stratosphere, troposphere, SST modes because of that shared variance. It also has some diversity of ENSO contained as well between East Pacific ENSO and Central Pacific ENSO, which vary in their period and frequency as well, but both are captured well by these modes. And then our MJO would be around here, internal to the troposphere, and a period of around 57 days or so. This is the spatial pattern for heating for the MJO, and then before, I don't think I mentioned, but this was a spatial pattern for SST, which looks very much like classical ENSO. Okay, oops. Okay. Oh my gosh. All right, so moving on to forward integration, which is how we get all the extra model data points that we'd like to use for this study. So we're following a study from Penland and Metrosova again, where we integrate forward in time to give a free-running limb state vector, x, which is length 365,000, so 1,000 years of daily data. I won't get into too much detail about everything that's going on in this equation, but the biggest part to know is that we use a delta of 1/24 days, which is 1 hour time steps. This portion here is our observed statistics, and this portion here is the noise. And it also features randomly generated numbers, which have unit variance and are normally distributed. And other variables like Q and eta are eigenvectors and eigenvalues of a variable that's capital Q, which is the covariance matrix of white noise forcing. And after we integrate forward in time, we can use the same filtering methodology as before to isolate the processes again. And also the summation indices are over I and J, which are the 49 EOFs that we kept. Okay, so moving on to some of our results. The first plots that I'm going to show are the power spectra that we calculated. We used a Hanning window with 1,000-day segments, and these plots kind of tell us on what time scales the majority of the variance in power is being contained for each variable. So if we look at the power spectra for our first two variables in the state vector, SST and Q, we're plotting the power for the first 3 PCs. As we can see here in the first row, ENSO is pretty well captured in the first 2 EOFs, and also since ENSO indices are typically derived from the first 2 EOFs, that's a really good sign as well. The peaks are pretty low frequency. They would correspond to a frequency of around 500 days, which is also representative of ENSO timescales. And also these peaks are within that stratosphere, troposphere, SST space, which is where we expected to see ENSO. So yes, that's where most of the power is. In our second row here, in this first PC, we see both ENSO and MJO signatures here, captured by the stratosphere, troposphere, SST space, as well as the internal troposphere space. The frequencies at which they're peaking are different too, which kind of reveals to us the timescales that these are occurring, and confirms that ENSO would be over here with a lower frequency, and a slightly higher frequency would be MJO, which would correspond to a smaller amount of days. And then also the second and third PC for heating are very internal to the troposphere, as seen by the low power in every other filter and the very high power in the internal troposphere space, and the full spectrum, which is plotted in black. If we move on here to our zonal wind and our stream function, so the first 2 principal components for zonal wind, we see that pretty much all the variability is captured in the internal stratospheric space. But something much more interesting happens in the third principal component, where we see a lot of power peaking in that coupled space, the stratospheric, troposphere, SST space. So that's something interesting that we'll explore briefly in the next slide here. And also, so down here for stream function, we see that all the peaks are pretty much internal to the troposphere. This kind of makes sense given that the stream function was calculated at 750 hectopascals. And also, you've probably noticed that a lot of times the filtered power exceeds that of the full space, and this again highlights the non-orthogonality of the filters and how they kind of interfere with each other. So if we look further here at the third principal component of zonal wind, and we plot the spatial pattern for the third EOF, we can't really say a ton about what's happening here, but we do know that when one part is increasing, the other is decreasing. Signs are arbitrary, but another thing to note is that because oftentimes the first two PCs of zonal wind are used to develop the QBO index, the fact that there is this kind of shared variance between the stratosphere and the troposphere in that third one raises the question of whether or not this should be considered for developing QBO indices. Okay, and then moving on to our Hofmuller plots, which are going to be time versus longitude plots. And if we plot these using the filtered data, we can see how properties of our systems are progressing through space and time. The overlap between ENSO and MJO signals kind of provides an interesting obstacle here for us to work with. We can either look for events that are strong in magnitude in both ENSO and MJO and see kind of like what patterns are dominant and which are getting washed out. And we can also look for ENSO neutral cases to try and kind of remove the effects of ENSO and see what's happening there. The events that were picked out for these were chosen based on phase space diagrams of the MJO, which uses a unit circle, and everything that's outside of that unit circle tells us whether or not it was a strong MJO event. And we also used NOAA's extended multivariate ENSO index, which ordered ENSO events based on how strong they were. So we kind of picked out ones that were on the stronger side towards the top of the list. And these were also made plotted using only boreal winter data. So first we have plots for sea surface temperature during the 2008 season, which corresponded to a strong La Nina event as well as strong MJO activity. So we have SST plotted in three of our filters here, as well as the full unfiltered space. In the tropospheric internal space, so we can see the MJO's impact on sea surface temperature, which is given by this kind of patchy alternating signal over time between positive and negative anomalies, as well as in the stratospheric troposphere SST space up here, we see this long persistent signal of cold SST anomalies, which align well with what we would expect during a La Nina season. And if we add all these filters together, we should get the unfiltered space here, but there's also that level of interference that's occurring, which kind of affects the magnitudes that's happening. So if we do the same thing, but for heating, we can see very clearly here in the internal troposphere space the MJO's impact. And the fact that it's so patchy too kind of highlights that this is happening on like the interseasonal shorter time scales, which should be compared to ENSO's effects, which are much more persistent and kind of go across that whole season. Also, the fact that these anomalies are sloped kind of show that the pattern's moving eastward, which is what we want to see with the MJO since it's propagating eastward. And then also in the unfiltered space, we can see that the most dominant pattern here is a lot closer to what the MJO pattern looked like, with, of course, some interference happening in the space where ENSO is. But it's kind of interesting to see that in the full space for SST, what ENSO was doing to SST seems to be having the biggest impact, but for heating, it resembles the MJO a lot closer. And then if we make these plots again, but for zonal wind, we can actually isolate exclusively the 50 millibar zonal wind in our data. which is really helpful to see. And if we look here in the internal stratosphere space, which is where the QBO would be, these really persistent negative anomalies indicate that it's an easterly phase of the QBO. And there are some very small contributions happening from both the internal troposphere space and the stratosphere-troposphere SST space, but overall it's having a pretty low effect on the full unfiltered data, which resembles the internal stratosphere space very closely. So, like I was saying earlier, if we make these plots again, but look at an ENSO neutral season, but still where there is strong MJO activity, we can still see the MJO's impact on SST down here in this panel. But when we remove ENSO, we get rid of that long persistent signal, and the anomalies we see here are a lot smaller in magnitude. And then overall, there is a pretty big amount of interference here, but it does not resemble ENSO signals really at all in the unfiltered panel. And then looking at heating again, we would expect with strong MJO activity to see the MJO signal here, which we do, with very, very strong heating anomalies. That's having definitely the biggest overall impact on the unfiltered heating space. Whereas in the space where ENSO would typically be, we see just kind of like some smaller in magnitude, kind of like patchy anomalies. I'm not really sure what's going on there. So here the MJO kind of reigns supreme. And then finally, looking at zonal wind activity again, negative anomalies indicate that this was also a season where there was an easterly phase of the QBO. And then even when we do get rid of ENSO, we see amplitudes of zonal wind anomalies in the space that are comparable to what the anomalies look like in the space during an ENSO year, which is interesting. And then also, again, looking at the persistence of signals here, since we see blue all across time, it kind of gives us insight into the timescales we're looking at. So on QBO timescales, obviously, we're talking about longer periods of time. Okay, so moving on to our next form analysis, composite maps. So with these, we can make time average composites that show spatial patterns in the data. We can analyze variables throughout specific phases of ENSO and QBO using derived indices. So if we kind of just take a sanity check here and look at SST and heating during warm El Nino phases and cold La Nina phases, the ENSO phase was defined using the first SST EOF, which typically corresponds to a Niño 3.4 index. And then we kind of slice them again to show only tropical latitudes and using only data from that linked strat-trop SST filter. And the patterns we show here are pretty much what we'd expect with the warmer anomalies during El Nino and cold anomalies during La Nina. And then also it's important to note that the shape of these patterns is very dependent on the index being used. So it's a lot more difficult to kind of assess the diversity of ENSO events that's happening here, especially given that we're averaging over long periods of time as well. But if we take this one step further and select only ENSO neutral years, but look at what it looks like during an easterly versus westerly phase of the QBO, where we define a QBO phase using zonal wind data, looking at whether or not zonal wind is greater than 0, which would be westerly phase, or less than 0, which would correspond to an easterly phase of the QBO. We do see some interesting patterns here. It appears that both SST and heating anomalies are stronger in magnitude during the westerly phase, but it is quite difficult whether to say this can be attributed to the QBO because the QBO wind and temperature anomalies do not really travel significantly below the tropopause, and these composites were also created using the existing record of data, which means that with more data over longer periods of time, this could very well just be, something that gets washed out. And some other features we can point out here, that the anomalies are kind of similarly signed over the Pacific Ocean, but look a little bit different over the Indian Ocean and maritime continent. So if we actually create these same maps, but now use the climate run data, which was our data that we integrated forward in time to get these more data points, and we look at the same thing, the easterly versus westerly phase of neutral ENSO, we see that these patterns get very, very weak. I use the same range to kind of compare better, but it's really hard to say, but it even almost appears that these anomalies are slightly stronger in the easterly phase now, whereas before it looked a lot stronger in the westerly phase. So we can kind of conclude from this that by adding all these samples, it's hard to say from the existing record whether or not the QBO is really affecting what SST and heat would look like. Okay, so now if we plot zonal wind, but divide it by ENSO phase as well as QBO phase, we can look at some very interesting activity here. In the easterly phase for El Nino, we see some asymmetry about the equator with some very low anomalies here, kind of north of the equator. And this is not present for the westerly phase of the QBO. And we also see, if we make these again with the climate run, we can see how these patterns change pretty significantly. That asymmetry we saw before in the existing record, now we see more positive anomalies here north of the equator. We also see that the band of positive anomalies around the equator in both the easterly phase of neutral ENSO and La Nina, so down here, these bands are getting a lot narrower and kind of more concentrated here close to the equator. Also, the westerly QBO phase of La Nina becomes more asymmetrical than it was before, where the negative anomalies are kind of more concentrated up here and we see more positive anomalies below. And there's also stronger negative anomalies in the neutral phase for westerly QBO, where before it was very, very light, but now we see a clear signal here.
These are for the filtered, right?
Yes, these are for the filtered data set. So it was zonal wind values within the StratTrop SST data set, but the QBO phase was derived using the unfiltered data. Okay, to kind of summarize here what we learned today. So the observed patterns that we saw in the Haber-Muller diagrams are a very distinct response to the ENSO, QBO, and MJO events that are occurring at this time. The filtering methodology that we use gives us a lot of insight into the portion of the data that is connected to the stratosphere, where we see that the impact from the stratospheric zonal winds are contained in the subspace. We saw that forward integration helped a lot with the scarcity of data points and tended to reveal different patterns than what we saw in the existing record. And also our power spectra plots kind of suggest that the variability coupled to the stratospheric zonal winds are at primarily low frequencies. Additionally, we saw that during both active ENSO and MJO seasons, ENSO had the greatest influence over SST, while MJO appeared dominant in the heating. But this was kind of not the case in ENSO neutral events. The contributions looked a lot different. We also looked at the spatial pattern for the third EOF of zonal wind, and although we can't say much about it, it could definitely be a major player moving forward in QBO research and how we derive a QBO index. And also the non-orthogonality over filtered subspaces, where we see interference that affect the overall total here, kind of highlights the importance of why we would want to use LIM in the first place, because using different models, we might not be able to kind of separate these processes and the coupling. So the next steps here for our research, we would like to examine the third EOF of zonal wind further, kind of figure out what's going on here, create different LIMs for different time periods, notably pre and post satellite era, to assess kind of how these correlations were changing, like we saw in the ENSO QBO link. We can also use LIM to assess how different wave frequencies are impacting the MJO-QBO relationship. If we use different ENSO indices, we can explore the role of ENSO diversity and how these patterns look different, as well as using extratropical LIMs, so we can look at the effects of teleconnection patterns. And then I would like to acknowledge my advisor, Dr. Stephanie Henderson, for taking a chance on me and fostering such a love of science and discovery and all that. My committee members, Angel and Dan, who could not be here today. Pete, for always coming through with all the tech help. And Professors Maroon and Zanowski, I would not have learned to code without you. I feel a lot more confident in my coding abilities. And all the wonderful AOS friends I made who came today. And with that, I will take any questions.
All right, do we have any questions from the students?
Rachel?
Great presentation, Juliana. I had a quick question about the heading window you used for power spectrum analysis. I was wondering, did you try a smaller window and see if the peaks changed, or do you think that might affect the results, or not much?
I think it definitely could. The Hanning window I used was based on, I think, one of the papers that Steph wrote where she used the same thing. I'm not sure if she also explored different size windows, but yeah.
It's been too long.
I don't know if it would change like super.
I know that different power spectra, like different window types, did not make a difference. I remember doing different window types, but I don't remember. I don't think it would make a difference, just because it makes physical sense what the results are.
Thanks.
Great presentation. Can you go back to the few slides before the summary?
Sure.
Yeah, right here. So, how do you define the QBO effects, like the westerly and easterly?
Yeah, so we used zonal wind anomalies for 50 millibars and looked for anything that was greater than 0 was the westerly phase, and anything less than 0 was the easterly phase. But I know that other indices use like 0.5, but this was just kind of like a simple one that we derived.
Yes, because in the La Nina event during the easterly QBO, it seems like at the equator, around the equator is westerly wind.
Yeah.
Yep.
Yeah,
No, remember that this is the filter data, right?
Oh.
So the QBO is in the internal stratospheric data. So this is only showing the part that the troposphere and SST can influence, right? So what this is saying is like the La Nina is having an impact in the stratosphere that's leading to these westerlies, which agrees with that composite that you showed earlier, where you have during the 1997, 1998 La Nina, in the filtered space you actually had westerlies, but in the internal stratospheric space we had easterlies, which was an easterly QBO. So when you add them together, the effect is that you get a weaker easterly QBO. So it would actually weaken the QBO that you see. Yeah, so it's important to remember this as a filter. Yeah.
Really cool stuff. LIMs are such neat tools. You've done a really cool job doing this. I was wondering if you or anyone else has done some, so you kind of do the composite analysis versus east to westerly QBO phases. But has anyone looked at like the transitions from east to west or west to east and use those as compositing? Because that's a very predictable thing, right? You know it's going to happen because the QBO is just so very regular. It might be a weird thing to look at dynamically because the SST and the convection are going to change, but I was wondering if anyone had tried that out.
Yeah, nothing that I came across, but that would be
That was
super
a brand.
interesting.
I mean, this is kind of the first time that this relationship is being looked at using them. So there's really nothing out there. Lots to do.
Never escape.
There's a
Just
question.
wondering, I'm not so familiar with LIM, so I'm kind of coming from a little bit broader perspective. Like, what are kind of the new things that we've learned about how these things are related from this analysis?
Yeah, I think,
Like, coming back to your title, sort of.
Sure.
What's the, like, 3 cents?
sure. I feel like the biggest thing is kind of the fact that these patterns are kind of changing a lot when we add model data. So it's kind of hard to say definitively, like, this is what this would look like during westerly QBO phase or easterly QBO phase, because things are changing a lot over time. Also, I would probably emphasize the role that the filters play, and kind of say that these relationships are so intertwined that I feel like using the filter to separate them is kind of like a necessary form of analysis, which I feel like is not really captured super well in other models. And this goes back to like the non-orthogonality.
So what have we learned about how the QBO, ENSO, and MJO are related? That's what I'm asking about.
Sure.
Like, what's the, have we learned something? What's the 3-sentence summary?
I mean, I think that we've learned that there's a lot of like overlap in signals. I don't know if like I could say anything like this says this or this says this, but I feel like perhaps it maybe raises more questions than answers of stuff we could do going forward.
There are some things so that I think we can say so far. So for example, we know that any relationship between ENSO, QBO, and MJO has to be within that what you call the stratosphere troposphere SST subspace, because that's the only, those modes are the only ones that capture variance across the stratosphere, troposphere, and SST. Right? Everything else is internal to the stratosphere, so there's no variance to the troposphere. Then there's the internal to the troposphere, so that's just, you know, processes that are that don't that where all the variance is within the troposphere. So the whole idea between this filter is that any relationship between these would be captured within this filter, right? So for example, the fact that we get the westerly anomalies during La Nina tells us that the La Nina is forcing westerly anomalies in the stratosphere. And then so this goes to like the future work where we want to separate the time periods to say, do we see this shift in the correlation, and can we use the subspace to try to understand why? Because there was work that looked at it and said, oh, La Nina forces westerly anomalies, but that depends on the time period used. So we can isolate that. You can't isolate that in any way. Another thing that I think is really cool that you talked about was the power spectra. So if you go, can you go back to your power spectra plots?
So just to kind of restate that, so it tells us about, it kind of gives us hints about how this process of ENSO influencing QBO works.
Yes.
And we know it has to work through the stratosphere.
So it has to be, and it can be isolated within the subspace. So there's definitely, like Juliana said, a lot more work that we want to do. But this gives us a method to look at it in isolation, which is really hard to do otherwise. So,
It decided
it just
would
kept
like
going.
to-
It just keeps
Yes.
going. It's okay. So
manually pick it out.
So one of the really interesting things is, you know, there's a lot of focus on like QBO impacts, but that stratosphere, troposphere, SST subspace is actually not at all explained by the first two EUFs of zonal wind in the stratosphere, which is often used to define a QBO. That's one way you can define the QBO. And the QBO was that single QBO mode internal to the stratosphere. The third EUF is actually what's coupled. right? So that tells us that, hey, maybe we can use a third UF to try to kind of examine what actually does have an impact on the MJO and what ENSO actually has an impact in the stratosphere. It also tells us that it's all really long time scales. You see within the power spectra and also some of the composites, you get this really persistent signal throughout an entire season, or in the power spectra related frequencies, right? So in the composites, one thing that was interesting is that in the neutral ENSO case,
A
so
little
here,
weird, but
yeah, so the blue here is the stratosphere troposphere SST, which is what actually communicates across these regions, whereas the green is internal to the stratosphere, so that's the QBO, right? So the first two UFs are entirely explained by the QBO. And then what actually you see communicate to the troposphere and SST is actually here. And that's really interesting because most people focus here.
So that would tell you something about what processes and models, you could use that to improve numerical models somehow, right? Or
I mean, I
improve
think
diagnostics
it's
for numerical models, or?
it's difficult because models just do such a bad job at getting the QBO in the first place. The QBO requires.
Well, this is like they need to get EOF3
They
too,
do,
and
right?
maybe people are only looking at EOF1 and EOF2.
Yes. Yeah, exactly. But any stratosphere zonal wind anomalies may be related to similar processes, which is like the waves. I mean, we don't really know much about this. Like, is it also driven by waves? I would think, but who knows? It could be influenced by the exotropics. I don't know. Hence why that's in the future work.
There's actually two questions online. Evans Meeker says, great talk. I was wondering about the relative contribution to variance of the third zonal wind EOF compared to EOFs 1 and 2.
sure. Oh, actually, is this what he was referring to as well?
That I don't know.
No,
They're going to be a few seconds.
The UFs themselves.
I was wondering about the relative contribution to variance of the third zonal wind EOF compared to EOFs 1 and 2.
Oh, okay. So, it was like a cumulative percent that we calculated. So, I forget off the top of my head how many we kept for zonal wind. I think it was either 30 or like 7. But, I can't imagine it was like a ton.
If you go, do you mind going to the figure that has UF3?
Oh, for sure.
Maybe. I know the first UF explains the most, right, by definition, and it's a really large percentage. I mean, we kept only 4 EOFs, and that was 97% of the variance in the stratosphere. The stratosphere just does not vary very much.
Yeah, he's just pointing out that the power on EOF 1 was like 10 to the 11th versus 10 to the 6th for EOF 3, so it's quite a bit less in terms of the total on the y-axis.
We saw it briefly.
Yes.
Yeah.
Yep, that's right. I don't remember what the percentage was though. But it's definitely smaller. Yeah.
His other question, he says, question about the filtering. It looked like the variance in zonal wind was highly constrained to a few eigenmodes. Does that hint to a limited relationship between stratospheric zonal wind and SST and heating?
I think I can pull that one up, hopefully. Oh.
Oh, it keeps going. Oh no.
She's so close. In the meantime, could you repeat the question one more time?
Sure. It looked like the variance in zonal wind was highly constrained to a few eigenmodes. Does that hint to a limited relationship between the stratospheric zonal wind and SST and heating?
yes. Because as we can see here, like where it does have variance is in fact, yeah, there's only kind of a couple between like 40 and 50. But I guess the fact that it is like so well contained in the short number of nodes kind of like begs the question of we should look into those specifically. And those are kind of like incorporated into the filter that is coupled. But yeah, that would definitely be something to kind of like look further into to see just like kind of assess how much it is having an effect.
Does it mean just like the number of modes? Is there less modes relative to the troposphere?
A limited relationship. I don't know.
I mean, this is all, so here you can see like this is all internal, right? And there's a lot of modes that explain internal variability, including the lower frequencies. Whereas here you have the, an increase in blue means you get an increase in SST variance, so ENSO would be within these. This is QBO right here, right? It's entirely internal to the stratosphere, right? There is zero variance in everything else. It is entirely only in the zonal wind, so it's internal to the stratosphere, whereas what we call the coupled, the stratosphere, troposphere, SST are these that have variance in all of them. Right, so you can see like they're kind of more in the middle. They all add up to 1, right? So where you kind of see this variations across all of them. So there is going to be a more limited number, just because you have a lot less. You have a lot more, a broad range of frequencies and a lot more variability in the troposphere. I don't know if that answers this question. Any other questions? All right, well, let's thank Juliana one more time. Thank you so much.